reheat Rankine cycle. One of them promise in increasing the efficiency of the ideal Rankine cycle. So we saw just simple Rankine cycle. To improve this Rankine cycle, in the example also we saw 16%. Usually it is 30 to 40%. To improve this, there are many various steps or various measures being taken or various modifications are being done in the Rankine cycle so as to improve the efficiency of the cycle or thermal power plant. A two-stage turbine. So earlier we saw only one stage. Here we'll see a two-stage turbine with reheat in between is the solution to the excessive moisture problem in the turbine and is commonly used in actual steam power plants. The sole purpose of the reheat cycle is to reduce the moisture content of the steam at the final stages of expansion process. The difference between the simple ideal Rankine cycle and the ideal reheat cycle is that expansion process occurs in two stages. In first stage, high pressure stage, the steam expands isothermally to an intermediate pressure and is sent back to the boiler where it is reheated at constant pressure to the first initial temperature. In the second stage, the low pressure stage, steam expands isothermally to the condenser pressure. So I'm showing here in the line diagram. So first one, the boiler, last time seen only one turbine. Here after expansion, it is instead of direct taking to the condenser, sorry, it is taken back to the boiler to be reheated. And after reheat, the steam is taken to the low pressure turbine wherein sorry, the pressure steam again expands, means and then it is being condensed into the condenser and been fed back to the boiler for regeneration of steam. So you see that the expansion of the steam is taken in two stages so that the content of the moisture is reduced as well as the heat from the steam is extracted in two stages so that the efficiency of the thermal power plant increases. In line diagram, on TS diagram, you just see 1 to 2. Here it is shown 1 to 2 pumping action. You are seeing here in the TS diagram, constant volume cycle, you can say approximately constant volume, or you can say constant entropy. Yes. Okay. Then 2 to 3, you can see the constant heating at constant pressure taking place in the boiler, and 3 to 4, expansion in the first stage, that is high pressure, or you can say intermediate pressure turbine. Then it is reheated. This reheated process is shown by the process 4 to 5. At this stage, the steam is from the first stage is being taken to the boiler where it is reheated. Up to 5 means they superheated up to the initial temperature, that is as 3 noted. Unless and it is mentioned, it is, you can say that it is reheated to the temperature to the original steam. Then it in the second stage, it is again expanded in the second stage turbine so as maximum work output can be extracted from the steam. And then from 6 to 1, condensation takes place in the condenser and the cycle continues. Okay, this is about the reheat cycle. The again formally you can see just little fast. The total heat input and the total turbine work output for a reheat cycle become Qin is equal to Q primary plus Q reheat. That is, you can see from the diagram itself, H3 minus H2, okay, plus H5 minus H4. That much is the heat is supplied to the steam. Then work out turbine output is equal to work turbine high pressure, plus work turbine intermediate pressure or low pressure. So therefore it will be in terms of enthalpies H3 minus H4 plus H5 minus H3 minus H4 plus H5 minus H6. And it is written double. Okay, a single reheat process in a modern power plant improves the cycle efficiency by 4 to 5% by increasing the average temperature at which heat is transferred to the steam. Okay. Now, one numerical on the reheat cycle. Sorry. A steam power plant operates on an ideal reheat cycle, Rankine cycle. Steam enters the high pressure turbine at 8 megapascal and 500 degrees centigrade and leaves at 3 megapascal. Steam is then reheated at constant pressure to 500 degrees centigrade before it expands to 200 kilopascal in the low pressure turbine. Determine the turbine work output and the thermal efficiency of the cycle. So a line diagram is drawn here again. This is the reheat cycle shown here, and this is the reheat cycle on TS diagram. So we'll start directly in solution, and as told, first you have to write the data, and then from the data you have to try to find out all the values of enthalpy first, and then the formulae put up in the formulae so that you can find out the required things. Okay, step 1. Okay, values in color obtained from Mollier chart. So whatever they have colored here shown, they are either obtained from Mollier chart or steam table. And I had told minimum 2 to define the state of the system, minimum 2 points to be known. In the bracket, it is 2 points which are known are written. So P1 is equal to 20 kilopascal. So let us start. So here it is P1. Okay, P1 means here last at the pump inlet, you can say. It is the pressure 20 kilopascal. Drainage pressure at point 1 is 0. H1 is equal to HF1 is equal to enthalpy. So we know the condition of the steam, X is equal to X1 and P is equal to P1. You can directly find the value of HF1 is equal to 251.5. Then S1, similar way from the steam table, 0.8321. Step 2, P2. P2 is the higher pressure, which is given 3 megapascal. Sorry, which is given 8 megapascal. That is 800 kilopascal. You can directly write in terms of kilopascals also, so that it will be easy to while solving the problem. S2 is equal to S1. Just told pumping action, entropy almost remains constant. That S2 from SF1, we know we can get it the value of S2 equal to S1 directly from the steam table, 8.8321. Enthalpy H2 is equal to, now you know the two conditions, pressure P2 and entropy S2. So at pressure P2 and S2, you can directly find out the value of enthalpy at state 2 is equal to 259.6. Stage 3, P3 is equal to 800 kilopascal. Now you are coming to the state 3, 1, 2, 3 here. So at state 3, P3 is being taken as how much given? 800 kilopascal. Okay. We'll see it later. Okay. P3 is given 800 kilopascal. At state 3, P3 is equal to, actually this P3 is equal to, okay, 800 kilopascal. T3 is 500 degrees centigrade. It is given, I think. Yes. So reheated at 500 degrees given. So T3 is equal to, we'll see here, state 3, where it is gone. So H3 is equal to Hg, enthalpy of the steam at T is equal to T3 and P3 from superheated steam table. You will get the values 33991 kilojoules per kg. And S3 is equal to Sj again from superheated steam table. You will get the value 6.724. P4 is equal to 3000. It is expanded up to 3 MPa. That is 3. So state 4 is given. That is 3000 kilopascal or 3 megapascal. Okay. So at pressure P4 here. Now we don't know the condition. What is the condition of the steam at 4? So one more is given. S4 is equal to S3. Yes. Yes, super 4. Yes, super 4 is equal to, you know, this condition, 3 megapascal, isn't it? 3 megapascal, you are getting the values you are getting the values of S3 from the steam table, and that therefore S3 will be equal to, that S super 3 is equal to S super 4, and that can be obtained from the steam table with the help of S super 3, that is we 6.724. Okay. Here we can write it as, then we'll state 5, we'll see. Therefore, enthalpy at stage 4 is equal to S super 4. You are knowing the two values, pressure P4 and S entropy S4. You will get the value from the steam table, 3104 kilojoules per kg. State 5, P5. Now we can going again P5. It is again reheated, and they taken to the original conditions, that is 3000 kilopascals, and T5 is 500 degrees centigrade. Therefore, knowing the two conditions, you can find out the value of H5 from the steam table, that is H super 5 is equal to 3457, and S super 5 7.234 kilojoules per kg Kelvin. Then state C is a P6, that is condenser. So S6 is equal to S5. Now you can find the value of S5 already calculated, 7.234. Then you are knowing the two. Now you can find out the value of X with the help of this SF. Enthalpy you can find out is with the help HFG6 is equal to HF1 plus X of HFG1 or HFG6, you can say, at the same pressure, that is then, but we don't know the value of X. You can find out the value of X with the help of entropy. SC is equal to X5. S6 is equal to S5. From that, you can find out the value of X. Now, before that, what are the asked? Turbine H3 minus H4 plus H5 minus H6. H3 minus H4 plus H5 minus H6. Qn is equal to H3 minus H2 plus H5 minus H4 reheat. Okay, and heat supplied, that is taken. Then turbine efficiency is equal to work of turbine, neglecting the pump work direct upon heat supplied. You can take sometimes. Therefore, turbine work output is equal to H3 minus H4 plus H5 minus H6. All the values are we got here. So here, instead of going that I told here, H6 we have got directly from 2 points. P is equal to P6 and S is equal to X6. From these 2 points, you have find out the value of 2385 kilojoules per hour. There is an alternate method that from the entropy, you can find out the value of X first and then substitute the value of X here. You will get the value of H6. Okay. Here it is taken directly from the steam table, no problem. Okay, so now we can just substitute all the values of it in the equations, and you will get the values. So W turbine is equal to S3 minus H4 plus H5 minus S6. You will get the value 1367. Heat supplied, we get S3 minus S2 plus H5 minus H4. You get 34325.4. Now, if you divide, get the thermal efficiency W turbine upon Q in, neglecting the pump work done on the pump, you will get the value 39.82%. You have seen in the first we got some around 17%, improved a lot, but generally around 39 to 40% of the efficiency we see with the reheat cycle. So this I hope understood. Then we'll go the last one, that is the Rankine cycle with regeneration. A simple little fast because this very fast and I have to explain with a little bit speed. Okay, in a simple Rankine cycle, heat is added to the cycle during process 2-3. You can see here 2-3, the heat is being added in the boiler. Okay, during the first stage, the temperature of the water is low. That reduces the average temperature during heat addition process. To remedy this shortcoming, increasing the temperature of feed water leaving the pump and entering the boiler can be considered. So in order to improve the condition of the water coming into the boiler, then automatically the more heat will be added at that the boiler or with less fuel, then this can be used for regeneration of the steam. Let us see how it is. Okay, then this is accomplished by extracting steam from the turbine to heat the feed water. So the feed water, the water which is coming from the condenser is cool, because we have cooled it in the condenser. If you directly take to the boiler, it will take more time and also more fuel. So it will be a loss of efficiency. So to overcome this, it is being preheated. The water is being preheated in, in the feed water, and then it is taken to the boiler. How it is preheated? This is preheated by means of taking extraction from the turbine. One pipeline is being, or a point is being taken and from the turbine, and part of the steam is taken to the feed water so that it is heated here. So this type of process is, we call it as a regeneration. Okay, so this regeneration process, now instead of I'm telling theoretical, directly go to the practical. So shown in the figure diagram here, and with the help of a TS diagram, I'll try to explain. So we'll see the 4 to 5. You see 4.4 to 5 is a heating of the steam in the boiler taking place at a higher pressure. So highest pressure, 4 to 5. Then 5 to 6 is the expansion taking place in the turbine. So part of the steam is taken, then taken to the feed water, and remaining steam is being then taken to the condenser after completion of work. So 5 to 6, you are seeing expansion. Uh, Actually, 5 to 7 is there. Expansion is taking place at 0.6. This is extraction is taking. This extracted steam is being taken to the to heat the feed water here at 0.3. Okay, here you are seeing between 2 and 3. Okay, then sorry, 7 to 1 is a, you can see this condensation taking place at lowest pressure, and 1 to 2 first pumping action at isentropic process approximately. 2 to 3 you are seeing here. 2 to 3 is being heated. Before, earlier it was directly taken to the 0.4 to the 0.5. So 2, 4, 5 earlier was taken. You are seeing here 2, 2-3 or 2, 4 or 2, 2- might be here. So 2, 2-3 here at intermediate some pressure, the water is being heated at 0.3. You are seeing, means 0.3 means it is heated at 0.2. When the water comes from pump 1, and at 0.2 you are seeing the steam is entering in the feed water. There is a tube shell type, indirect contact type of this feed water heat exchangers are. Then after heating, the water goes to the pump number 2, wherein it is pumping action 3 to 4. 3 to 4 again is taking pumping action here. Then again it is being heated in the boiler. In this way, this cycle is of regeneration. So part of the steam is being extracted in the feed water so as to heat the preheat the water before going to boiler. Okay, so that adds into the efficiency of the plant. Okay, so this is about regeneration. So at the timing less, in next class I will explain in detail again about this actual in thermal 210 megawatt where I work, and we were having this modified Rankine cycle, we call it as, and this based on this. In with fast, I will just again to tell 1 to 2 is the pumping action taking place with the help of one pump. Again here, these are, you are seeing extraction 4, 3, 2, 1. This is a low pressure heaters. So at low pressure, the water being heated before going to the boiler. 3 to 4, there is another pump that is call it as a boiler feed pump. Just remember here, I will show this. 4 to 5, again this is 4 to 5 to 6 to 7. It is being heated in the boiler at higher pressure with by means of pumping through feed water pump. Then 7 to 8 is expansion taking place HP turbine, reheated with the help in 8, 9, and again it is finally expanded from 9 to 10, 10 to 11 by means of three turbines totally. Here you are shown two turbines. Okay, then there are so many extraction, 6 extraction shown, 5, 6. These are the high pressure extraction. That's why, and they are fed to the high pressure heaters. And these are the low pressure extractions, 4, 3, 2, 1, taken from the low pressure turbine. That's why they are called as low pressure extraction and given to the low pressure heaters, and high pressure extraction given to the high pressure heaters, so that the temperature of the steam is increased. So in the line diagram, in the actual diagram, we are seeing the turbine here. This is first turbine, second turbine. After first turbine, some of the extraction have been taken, and in the second also some of the extraction. So these are, you are seeing this is the LP heater. These are, you can see number 9 is, you can see the LP heaters. Number 10, you are seeing the HP heaters. So extractions, these are the extraction lines for 1, 2, 3, 4, 5, 6. You will be seeing the line 1, 2, 3, 4, 5, 6 something. So you can just observe it, and then after heating in this feed waters, low pressure heaters and high pressure heaters, then they are being taken to the boiler through the economizer for again steam generation. This is about the regeneration cycle. So numerical on the regeneration cycle, we'll see in the next or okay, just 5 minutes. I will just explain this fastly and will repeat it again in the next class. Note that the mass flow rate of each component is different. If 1 kg of steam enters the turbine, you can see I have again drawn this line diagram on myself. You can see the 1 kg of steam is going to the turbine. Then part of the steam is extracted to the feed water heaters, that is y kg you can say. Then 1 minus y kg of the steam going to the condenser, and this 1 minus y kg is being pumped to the feed water heater. Then this here y kg is being added, so that 1 minus y plus y, again 1 kg of steam is, 1 kg of water you can say here, and going to the boiler. So this is the cycle. Just remember, just given in view of this 1 kg of steam going part y and 1 minus y, like that. Okay, note that the mass flow rate is, say, if 1 kg of steam enters the turbine, y kg is extracted to the feed water heater, and 1 minus y kg continues to expand in the condenser to the condenser pressure. So if the mass flow rate at the boiler is m dash, then the mass flow rate of the other components are condenser, it will be m dot into 1y. In pump 1, m dot into 1 minus y. Feed water heater, it will be m dot into y plus m dot into 1 minus y. That will be m dot. So mass flow rate will be m dot to the boiler. And pump 2, automatically the mass flow rate will be m dot. For convenience, heat and work interaction for regenerative cycle, note again the formula here, important one, while solving the problems on regeneration, is expressed per unit mass. So the mass is not taken, you are taking 1 kg, you can say like that. Steam flowing through the boiler, they are heat input is equal to Q in. Here at boiler, you will be seeing H5 minus H4. I have not shown here this H5 minus H4. Or you can see the previous diagrams, you will find out H5 minus H4 here. Here we'll see that H5 minus H4 will be the heat added. So this cycle, consider this cycle, then only you get understand this formula. H5 minus H4, Q heat output at condenser, condenser will be 1 minus Y instead of this, and 1 minus y into bracket H1 minus H7. Then the work output, turbine output is equal to H5 minus S6 plus 1 minus y into H6 minus S7. So again, you have to see that Rankine cycle. Okay. Just remind it. Next class I will explain again this, repeat this particular. W pump is equal to 1 minus 1 y H2 minus H1 plus H4 minus H3, considering that Rankine cycle with the suffixes. Open feed waters are simple and inexpensive and can also bring the feed water to saturated state. However, each feed water needs a separate pump, which adds to the cost. Numerical on the regeneration, the net power output of an ideal regenerative reheat cycle is 80 megawatt. Steam enters the HP turbine at 80 bar and 500 degrees centigrade and expands till it becomes saturated vapor. Some of the steam then goes to the open feed water heater and then balance is reheated to 400 degrees centigrade, after which it expands in the LP turbine or IP turbine to 0.07 bar. Determine the reheat pressure, the steam flow rate, and the cycle efficiency. Neglect the pump work here given. So from steam table of 80 bar, first you have to write whatever the you and 500 degrees centigrade. Write down the values of at state 1 here. Now suffix has changed here, but you remember at A1 you will be write down the values H1, that is S super 1 is equal to 339.8.3, S1, that is S super 1 is equal to 67.24 kilojoules per kg, S1 is equal to S2, that is 6.724 at 6.6 bar. So reheat pressure at, you can see it is a saturated, it is given. So at saturated pressure, if you know the value 1, now the two conditions are known, saturated and entropy. So 6.724 at entropy 6.724, the value of SG at 0.2, then if you know, we can find out the value of pressure. So the pressure directly you can get from the steam table is 6.6 bar. This is the first answer. Next, let H7 is equal to H8. Now you see the formula here see the cycle here. C7, this is the pump number 2, S7 and H8. H7 is equal to H8 and H5 is, this is pump number 1, H5 is equal to S6 as pump work is neglected. Therefore, S3 at 6.6 bar. So where it is the 0.3, it is 0.3, it is given 6.6 bar here. You have to write all the data first, then you can understand the problem. Okay, 6.6 bar means it is a constant pressure process. We have found out the value of S2, P2, that is the reheat pressure. Therefore, P2 is equal to P3. Here it is taken, it has a P2 is equal to P3. S3 at 6.6 bar, that is a P2. Okay, 6.6 bar and 400 degrees centigrade reheat is given, is 3269.3 kilojoules per kg. 400 degrees centigrade is given here. So reheated to 400. Here it is written 400 and 6.6 bar. You will get the value of S3 326.93. H2 is equal to H2. Already we got that is a Hg from directly saturated point and 6.6 bar, that is equal to 27.59.5 kilojoules per kg. Then now we'll see S3 at 0.3 S3, that is S super 3 and superheated condition. We know the two conditions, 400 degrees centigrade and 6.6 bar. S3 will be 7.6642 and S5. Now coming to 0.5, S5, where it is S5, the state of the 5 is SF, means water. So SF at pressure, low pressure at the lowermost pressure, that is given 0.07 bar is equal to 0.559, and S4 again at the low pressure is equal to S3, and we know the value of S3 here. Already we have written some 7.6642. So S3 we know, then S5 we know, and now we have to find S3 is equal to S4. So from that, so it is something written here. It is should be 7.717 here. Just correct it, and is equal to 0.559 plus x into 7.717. That is, value of x can be calculated with the help of entropy. S3 is equal to S4, and you know the value of SF5. From that you can find out the, and SFG also you know at the point pressure 0.074 bar, you can find out the value of x. So x is equal to 0.9207. Now from that you can find out the value of H4, that is H4 is equal to HF5 plus x of HFG4, that is 163.4 again from the steam table, plus 0.9207 into 2409 again from steam table, that is HFG4 with respect to pressure 0.07 bar, and dryness fraction is also known. So you can find out the value, and pressure is constant. Hence, you can find out the value of HFG from the steam table directly. From that, now we got all the values. H5 we got 17. So H5 we know. H4 we got. H6 is equal to H7. H6 is equal to H5 is equal to H6 approximately taken, and H7 is equal to H8. Okay, so H7, sorry, HF, H5 is taken as a H6 enthalpy because pumping action is there. H7 at a HF means it is a saturation line at 6.6 bar. It is 686.8 kilojoules per kg per second, kilojoules per kg. That is H8. Therefore, from heat balance, now this is the important step in the regeneration. M into H2 plus 1 minus M into H6. So M into H2. So yeah, the value M into H2, that is Y into this heat contained by this steam, extracted steam, plus 1 minus M. 1 minus M means this amount is going, and it is taken 1 minus M into bracket. What he has taken here? H6. So if you see here, so whatever the coming at the last, before the boiler, the value will be H6. Here extraction steam is steamy. It is added before that. That is the H6. I'll explain in detail next time. Just note down here M into H2 plus 1 minus M into H6 is equal to H7. Therefore, M is equal to 0.02016 kilojoules per kg of steam at HP. 1 minus M is equal to 0.7984. Therefore, turbine work done is equal to 1 into H1 minus H2 plus 1 minus M into H3 minus H4, because the extraction has been taken place. So that much amount of steam is heat is to be extract minus. That's why 1 minus M into H3 minus H4 is equal to 1347.6 kilojoules per kg. Considering WP negligible, heat in is equal to H1 minus H8. Here again see H1 minus H8 plus 1 minus M H3 minus H2. H3 minus H2, because part of some it is gone for regeneration. So remaining is H3 minus H2 in reheater. Okay. Where we are? Yes. So substituting all the values, and now we got, again I told write all the values of H, particularly H only, H1, H2, H3, H4, H5, H6, A1, so that it will be easy to find out the final values. So you have substituted H1, the value of H1, H2, H3, H2 with the value of M. We'll find, so heat in is equal to 3118.5 kilojoules per kg. Reheat pressure is equal to 6.6 bar. Steam flow rate is equal to 3600 divided by 1347.6. Now I have written the value directly, 1374.7.6. Okay, then is equal to 2.67 kg per kilowatt hour. Then cycle efficiency is equal to W upon Q, neglecting the pump pressure, pump work, 1374.6. That is W net we obtained. Here it is 1347.6. That we have taken here also. 1347.6 upon 3118.5 into, so total into 100% will be 43.21%. So this is about the regeneration. This is little bit taken a little faster. This I may repeat in the next class. I hope you understood the sample Rankine cycle with reheat, and Rankine cycle with regeneration, and the purposes for reheat and regeneration I also explained. So I hope you understood this particular class. Thank you very much.